Hello and welcome to the quintessential quantum mechanics lesson, position and momentum visualized with group theory. There will be a short MATLAB simulation at the end. This is Quantum Mechanics Mathematical Foundations Lecture 2 Part C. I'm Dr. Jacob Hudis. This series is suitable for interested science students from advanced high schoolers to physics PhD candidates. Commit to these lectures and master the fundamentals of quantum mechanics and its mathematical framework. Watch to the end for invaluable insight. And here's an outline for the adventure ahead. I'll begin with an introduction to the position basis. Then I'll discuss the generator of position shift or position translation. There will be a short discussion about the discrete Fourier transform. Then I'll move on to introduce the momentum basis. I'll discuss the generators of position translation and the momentum basis. Then there will be several slides dedicated to visualizing the Fourier basis. And at the end, there will be a MATLAB simulation written by Paul Mirsky. It's clear, clever, and extremely helpful for grasping these concepts. It's not fancy, but I think it's fantastic. Let's begin by introducing the position basis. In a quantum mechanical system, typically an atom or subatomic particle, one needs to define the possible positions a particle can occupy. These positions can be thought of as discrete boxes in three-dimensional space. A given system has a finite number of positions that an electron can occupy. So for example, let's assume this is an atom. The electron can be in any one of these boxes. If the electron is outside of this region, it's no longer bound to the atom has been ionized, it's not part of the quantum mechanical system. Let's start with a simpler example in one dimension to make the visualization easier. The ideas can be easily extended to 2 and 3D. In this example, let's choose 5 possible positions for our particle, arranged in a straight line. For this simple example, this is going to be the state space, and there's 5 possible states, which means there are 5 possible positions that a particle can be in. A particle can be in position 0, it can be in position 1, position 2, position 3, or position 4. And as you may know, it can be in any linear combination of them all. Now I'm going to discuss the mathematics of the position basis. Each position state is represented by a vector in the diagonal basis. This is vector x0, and this vector corresponds to a particle being at position 0. x1 has the 1 in the second location, and this vector means physically that there's a particle at location 1. x2 means there's a particle at location x2, and so on. This is a vector in the x basis, and each one of these values corresponds to a certain position in space. This is n equals 5, so there's 5 possible positions. If you had a larger system, this could be a 10-component vector or a 100-component vector, or it become a wave function, which is a vector with an infinite number of components. I also want to point out that the set of 5 vectors is an orthonormal basis of C5. Any vector in C5 can be written as a linear combination of these 5 basis vectors. I think that's fairly obvious because this is a diagonal basis. To model the physics accurately, we need to identify the operations that move a vector from one position basis state to another without altering the vector in any other way. These operations are known as the generators of position translation, or the generators of position shift. This is the generator of position shift, and if you act this matrix onto vector 0, it moves to vector 1. If you act it onto vector 1, it moves to vector 2. And if you act on vector 2, it moves to vector 3, and so on. This is used to model the motion of a particle in a quantum mechanical system. This is a permutation matrix, which proves to be very fundamental in quantum mechanics. To conclude with the position matrix, these are the position states. If I act the position shift matrix onto x0, that calculation is here. Here's the position shift matrix. This is x0. That produces x1. The position shift squared onto x0 gives you x2. Position shift cubed onto x0 gives you x3. This is the way that the position basis works. In quantum mechanics, we deal with the position basis and the momentum basis. The position and momentum basis are fundamental concepts. They provide the framework for describing wave functions and operations in quantum systems. The number of distinct momentum states is equal to the number of distinct position states in a finite system. Therefore, if a system has 5 discrete positions, it also has 5 discrete momentum states. And recall the position basis, these numbers tell you what position it's at. So this would be that you're at position 1 and position 2 and so on. There's also the momentum basis. Now the vector components tell you the momentum of the particle. This vector would represent a particle with 0 momentum. This vector would represent a particle with 1 unit of momentum. So that's the way that you interpret the position and the momentum. Are you in need of a great physics tutor? Dr. Hudis can help. Whether you're preparing for a high school test, AP test, or college exam, let me help you ace it. Are you an eager high school student aiming to get ahead and prepare for college-level physics? Or maybe you're a college student and you want to learn even more advanced physics? Dr. Hudis can help. Visit acephysics.org and schedule a lesson today. The discrete Fourier transform is a basis transformation. There exist 2 complementary bases for the space Cn. We are currently studying the example of the space C5. I can represent any vector in C5 as a linear combination of basis vectors in the standard diagonal basis. That's what we just did on the previous slide. Similarly, any vector in C5 can be expressed as a linear combination of another set of basis vectors, the Fourier basis, and this is what we're going to be doing on the next several slides. Ultimately, there exists two bases for this vector space, and the Fourier transformation is a basis transformation from one to another. In this lecture, we'll focus on understanding these two bases. We'll not delve into the details of the Fourier transformation. For more information on this, please check out my YouTube video on Introduction to Fourier Series and Fourier Transforms. Despite the challenging material, I believe it's presented clearly and effectively. It is a little long at 22 minutes. After 12 days, it only has 70 views and 4 likes. Please check it out and give it a like. There are two orthonormal bases of C5. This is simply a math concept. This is not physics right now. Any vector v can be written as a linear combination of these basis vectors in the diagonal basis. There is another basis of C5, and this is called the Fourier basis. This basis also spans the vector space C5. Let's not worry about the nomenclature right now. I'll get to that in future slides. Let's just look at these vectors. This has a factor of 1 over root 5 in front, and it's all ones. This vector has a factor of 1 over root 5 also, and this is 1, e to the I 2 pi over 5, e to the I 4 pi over 5, e to the I 6 pi over 5, e to the I 8 pi over 5. This goes in units of 2 pi over 5. This vector still has a factor of 1 over root 5 normalization condition, and this goes as e to the I 0, e to the I 4 pi over 5, e to the I 8 pi over 5, 12 pi over 5, and 16 pi over 5. This goes in units of 4 pi over 5. This goes in units of 6 pi over 5, and this goes in units of 8 pi over 5. Any vector in C5 can be written as a linear combination of these vectors. So the Fourier transform is just a basis transformation from this basis to this basis. From a conceptual point of view, now you know everything there is to know about the Fourier transform. It's a basis transformation from one basis in Cn to another basis in Cn. Here's an example demonstrating the two bases of C5. This vector v is some random vector that I chose. It has 5 complex numbers, and this v can be written in the diagonal basis, which is trivial. The v can also be written in the Fourier basis, and that's equal to negative 0.25 times this vector, plus 0 times this vector, plus 0.5 times this vector, plus 0 times this vector, plus 0.25 times this vector. The title of this slide is Position Vectors in the Position Basis and the same position vectors in the momentum basis. So now we'll learn what this nomenclature means. In the position basis, x0, for example, means that you're at position 0. x1 means you're at position 1. x0 here still means that you're at position 0. The blue and the gold are just positions in space, and they're the same positions in space. So this is position 0, this is position 0, this is position 1, this is position 1, and the difference is this is written in the momentum basis and this is written in the position basis. Both these vectors mean exactly the same thing. Both of these vectors mean that you're at position 0. But in the momentum basis, being at position 0 means that you're in all of the possible momentum states. You're in momentum 0, 1, 2, 3, and 4, and you're in a linear combination with a 20% chance of being in every one. Position 2 corresponds to this vector, it corresponds to this position. The vector 0, 0, 1, 0, 0 corresponds to position 2. Position 2 in the momentum space is the Fourier transform of this vector, and this has 5 complex numbers. All the complex numbers have a magnitude of 1 over the square root of 5, and they have a phase relationship that goes as 0, 4 pi over 5, 8 pi over 5, 12 pi over 5, 16 pi over 5. So what this nomenclature means, x1 means that you're at position 1. x1 subscript p means you're at position 1, but you're written in the momentum basis. So these are momentums, not position, but it still means that you're at position 1. This means that you're at position 2, but it's written in the momentum basis. We know the inner product of xi with xj is equal to 0 when I is not equal to j. On this slide, I'm going to take the inner product of x1 and x2 and show that they're equal to 0, but I'm going to do it where x1 and x2 are written in the momentum basis. It doesn't matter what basis the vectors are written in, the inner product has to be 0, they're the same exact vectors. This is x1 written in the momentum basis. Notice it's complex conjugate because it's the bra. This is x2 written in the momentum basis. If I take the inner product, the calculation is here. The sum of these roots of unity is 0. This is the magic that makes all of this possible, and therefore the inner product of x1 with x2 is, of course, equal to 0. AcePhysics.org, Math and Physics Tutoring with Dr. Hudis. On this slide, I want to discuss the mathematics of the momentum basis. To model the physics accurately, we need to identify the operators that move a vector from one position state to another in the momentum basis without altering the vector in any way. These operations are known as the generator of positions translation. The generator of position translation in the momentum basis is given by this matrix. It's a diagonal matrix, And along the diagonal is the complex exponential e to the I 2 pi alpha over 5, where alpha runs from 0 to 4. This is a 5 by 5 matrix because we're dealing with n equals 5. You could have any number of positions. If there were 100 positions in the system, this would be a 100 by 100 matrix. The 5 in the exponent would be replaced with 100, and alpha would go from 0 to 99. If you had an infinite dimensional matrix, then it would be a wave function. When this matrix acts on the position vector in the momentum space, when it acts on x0, it moves it to x1. And so it's moving. So this matrix is moving from position 0 to position 1, from position 1 to position 2. If I act the position translation matrix onto x0 in the momentum basis, it's equal to x1 in the momentum basis. This matrix is the position translation matrix. This is x0, and this is x1. If I act the matrix squared onto x0 again in the momentum basis, then it's equal to x2 in the momentum basis. The position translation matrix cubed is equal to x3, and that's the way this works. On this slide, I want to discuss how you visualize the position vectors in the momentum basis. So position 1 in the momentum basis is this vector. It has 5 complex numbers. They all have the same magnitude but different phases, and the phases differ by 2 pi over 5. So it starts out here. This is the 1. Then you rotate 2 pi over 5, comes here. You rotate another 2 pi over 5 here, another 2 pi over 5, another 2 pi over 5, and again another 2 pi over 5. You would be flat again. Now here's position 4 written in the momentum basis. Each of the complex numbers still has the same magnitude, but now they move with an angle of 8 pi over 5. So it starts here, and you go 8 pi over 5, 8 pi over 5, 8 pi over 5, 8 pi over 5, and 8 pi over 5 again to get back here. And this is an important picture in order to visualize these vectors. On this slide, I have them all written out. I also use this notation because maybe that way will help you understand it as well. This vector makes 0 full turns in the complex plane. x1 makes 1 turn. It starts here and it comes all the way around. x2 makes 2 turns, x3 makes 3 turns, x4 makes 4 turns, and this is the general picture that you want to have in your head of how these quantum mechanical objects look. Here I just want to tell you that the position and the momentum are complementary basis pair. So what this means is if you're at one position, let's say you're at position x0, that means that you're in an equal sum of every possible momentum state. If you're at one specific position, then you're necessarily spread out through all the momentums. That's what it means to be a complementary basis. I have another video called Pauli matrices and complementary bases. Near the end of this video, I do an example for the 2 by 2 case. Complementary basis works in both directions. So if you're at one momentum state, then you're spread out through all the position states. And it doesn't matter what momentum state you're at. On this slide, I do an important example where I demonstrate complementarity. I'm going to show that an equally weighted sum of every position vector or position value is equal to one single momentum value. In this slide, this is 1 over root 5 times each one of these position vectors. I'm going to choose to write these in the momentum basis. This is x0 in the momentum basis, x1 in the momentum basis, x2, x3, and x4. I can factor out a 1 over 5. The top term is equal to 5, so 5 divided by 5 is 1. And each one of these is equal to 0 because the sum of roots of unity is equal to 0. 1 plus e to the I times 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, that's equal to 0. 1 plus e to the 4 pi over 5, 8 pi over 5, 12 pi over 5, 16 pi over 5, 0. E to the 0, that's 1. 6 pi over 5, 12, 18, 24. And hopefully you can see how that works. Being in every single position value corresponds to one momentum value. Let's look at another example. Here's another equally weighted sum of position values or position vectors. The difference between this example and the previous example is now the phases of the complex numbers are different. Before they all had phase 0. Again, I replace the position vectors with their corresponding representation in the momentum basis. Then you multiply through by the complex exponentials. That's the matrix here. And on this page, this is the same matrix. I copied it over. And if you notice, everything in this line is equal to 1 because we have e to the minus I 2 pi over 5 multiplied by e to the positive 2 pi over 5. And it works throughout the whole line. The top is a sum of roots of unity. That's equal to 0. This is equal to 5 over 5. That's 1. Sum of roots of unity, 2, 4, 6, 8. 4, 8, 12, 16, 6, 12, 18, 24. Again, these are all 0. So what this shows is if you're in all the position values, if you're spread over all the position values, you're localized to one momentum value. This picture is helpful to understand complementarity. This would be for a two-state system. It can only have 2 positions and 2 momentums. If you're along the P1 axis, that means that you're an equal combination of x1 and x2. If something has some momentum, it's along this axis, then it has an equal amount of x1 and x2. And likewise, if you're along the x1 axis, then you have an equal amount of p1 and p2. All the ideas we've been discussing in this presentation are contained within group theory, and it's the group theory of the finite Heisenberg-Weil group. This group enables various manipulations of quantum states in finite dimensional systems. It has three generators: the position translation generator and the position basis. This shifts position states within the set of position basis vectors without mixing them into linear combinations. There's the position translation generator and the momentum basis. This generator also represents translations in position space, but in a different basis. And finally, there's the phase generator. This generator applies a phase shift to the quantum state. The Heisenberg-Weil group is a group used in quantum mechanics and quantum computing. This group has several important properties and applications, especially related to quantum information theory and signal processing. On this slide, I'm going to introduce the phase operator. For the n equals 5 case, the phase operator is a 5 by 5 matrix. It's always a diagonal matrix with the same entry down the diagonal. If n equals 5, it's e to the I 2 pi over 5, all down the diagonal. If I operate the phase matrix onto a position vector, I get a phase factor multiplied by the position vector. If I operate the phase matrix onto a position vector in momentum space, I get a phase factor multiplied by the position vector in momentum space. I can operate powers of the phase matrix to get different phases, so phase squared would give me e to the I 4 pi over 5. And for the n equals 5 case, the phase matrix to the fifth is the identity matrix. On this slide, I have the generator of position translation and the generator of position slide. We've already seen these before in this presentation. The position translation generator moves position vectors from one to another when the position vectors are written in the momentum basis. The position shift matrix moves position vectors from one vector to another when the position vectors are written in the position basis. What happens if we act the position shift onto the momentum basis or the position translate onto the position basis? This is the position shift matrix. It's acting onto x1 in the momentum basis. Position shift, x1 in the momentum basis. This is the answer, and you can factor out a phase. This is an eigenvector. It's the same vector, just multiplied by a phase. Here's the position translate acting onto x4 in the position basis, and again you get a phase. The position in the momentum basis is an eigenvector of the position shift matrix, and the position in the position basis is an eigenvector of the position translate matrix. This is the position shift matrix. When this acts onto a position vector in a position basis, it advances it from xi to xi plus 1. When it acts onto a position vector in the momentum basis, it just adds a phase, and that means that these are eigenvectors of this matrix, and so there's a symmetry there, and it's an eigenvector. This is the momentum translation operator. When this acts onto a position vector in the position basis, it adds a phase. That means there's a symmetry, and this is an eigenvector of this matrix. And when it acts onto a position vector in the momentum basis, it advances it from xi to xi plus 1. Finally, the phase matrix adds a phase, the same phase to every vector it acts on, and any vector it acts on is an eigenvector. Now I want to show you the MATLAB applet. This was brilliantly crafted by my friend Paul Mirsky. You can download this applet at symmetryoptics.com or email paulmirsky633@gmail.com. I will briefly discuss the applet and show its results now. In the next video, I will thoroughly discuss the applet and show you how to download it from symmetryoptics.com. Now I'm ready to look at a MATLAB simulation, and this simulation was written by my friend Paul Mirsky, who I studied physics and engineering with at Columbia University. In this simulation, there's the position basis in front and the momentum basis in back. You do the Fourier transform to get from the front to the back. The way he has it set up, this is position 0, this is position 1, position 2, -2, -1, and back to 0. It's slightly different nomenclature, but it's exactly the same setup that I was discussing in the presentation. And right now I'm looking at a system with 5 positions and 5 momentums, because that's what I was studying in the presentation, but we can change that number here, and I'll do that in a little while. First of all, notice if you're at one position, then that means that you're equally spread out through all the 5 different momentums. That's the way quantum mechanics work, and that's also the way a complementary basis in mathematics works. What are some of the operations that I can perform on this position state? Well, one operation I can perform is just to add a phase. And because there are 5 positions, there's going to be 5 phases. It's 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, and back to 0. And so what I want to point out is each one of these is a complex number with the same magnitude, and the phase can be read on the left. And if I apply a phase, that's causing, so now all of these complex numbers have the same phase, and it's the phase of 2 pi over 5. Now all of the complex numbers have the same phase, of 4 pi over 5. Another thing that I can do is I can multiply that vector by the position slide matrix. This button multiplies the vector by the position slide matrix, and if I do that, the position vector moves from one vector to another. It's still an eigenvector of the system, but now it moves from one to another. Now, this is the same vector just written in the momentum basis. You're still equally spread out over all the different momentum states. There's an equal probability of 20% to be in any one of the different momentum states, but the way that you can tell the difference between the two vectors is now there's a phase relationship. This is phase 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, and back to 0 again. And so this vector is obviously different than the previous vector. If I apply the position shift again, you get another phase relationship, and you can see the phase relationship changes. This is the Fourier transform. Now, one other thing that I can do is I can do momentum translation. And so this button here will cause a translation of momentum. And what that means is that's going to take each one of these momentum states and slide it over to the left one. But because there's momentum states everywhere, they're all sliding over to the left one. And that's the same thing as just adding an overall phase. And so the momentum translation in this case is just adding an overall phase because an eigenvector of the momentum translation operator is the position operator. Let's do 41 instead of 5. Now there are 41 possible position states and 41 possible momentum states. I'm not going to apply the phase matrix because I'd have to apply 41 times to get back to where I was. Let's do the position slide. If I do the position slide matrix, you can see that first of all, you're an equally weighted sum of every possible momentum state. There's going to be a 1 over the square root of 41 chance to be in each one of the momentum states. And if you do the position slide, you can see that the phase relationship is changing. I'm going to make another video. It's going to be a short video, but it's just going to be on using this simulation. And you can also download this and use this yourself, and you should. And so I'll go through that in the next video and explain all this to you in much more detail. AcePhysics.org. Math and Physics Tutoring with Dr. H. AcePhysics.org. Math and Physics Tutoring with Dr. Hudis.